Now we are ready to proceed to the next setting, combinations. But let's start with the following example. Suppose you are planning a road trip and you have 5 friends, but you can fit only 3 of them in your car. How many ways do you have to do it? Basically, we want to pick a subset of size 3 in the set of your 5 friends. And we are interested in how many subsets of size 3 do we have. Recall that elements of subsets are unordered. So we have to do something here. Let's start with some solution attempt. Okay, we can pick the first friend in 5 possible ways. Good. Now we can pick the second friend in 4 possible ways, because one of the friends is already picked. The third friend can be picked in 3 possible ways, so by the rule of product, there are 5 times 4 times 3, 60 possibilities. Is this correct, or is there any problem here? Again, observe that we counted the same option several times. Let's try to fix this solution. Note that we actually counted ordered sequences of friends. We picked the first friend, then the second, and then the third one. So it was ordered sequence. But we actually need an unordered group of friends. And note that each unordered group can be ordered in 6 possible ways. It can be ordered 3 times 2 possible times. And here is the list of all possible orderings of the group consisting of A, B, and C. And so, to fix this problem, we can just divide the previous result by 6. And that's enough. The actual result will be 5 times 4 times 3 divided by 6. That is 10 possible ways to pick 3 friends out of your 5 friends. Okay, let us introduce the general definition now. For a set S, its K combination is just a subset of S of size K. And the number of combinations is denoted in the following way and pronounced n choose K. So this is the number of K subsets of n element set. Okay, and we have shown in the previous discussion that 5 choose 3 is equal to 10. And let's depict this on the picture. So on this picture, we depict all possible 3 permutations. And in each column, we collect 3 permutations that consists of the same elements. So there are 3 factorial ways to permute 3 elements. And then the number of columns correspond to the number of 3 combinations. And the number of 3 combinations is 5 choose 4. And so we get that the number of cells in this table, we already know this is the number of 3 permutations, is 5 factorial divided by 5 minus 3 factorial. So then the number of rows times the number of columns is equal to the number of cells. So we have 3 factorial multiplied by 5 choose 3 is equal to 5 factorial divided by 5 minus 3 factorial. And this is how we have found what is 5 choose 3 equal to. Okay, combination is actually an important setting in mathematics, and we will need it a lot. But how can the number of combinations arise in data science? Here is an example. Sometimes you need to use a weak machine learning model that cannot in principle give a good prediction on certain sets of data. And one possible solution to this is to enrich the set of features by feature products. Suppose, for example, you have 5 numerical features A, B, C, D, and E in your setting. Then what can you do? You can try to enrich the set of features by adding new features that consists of products of any 3 distinct features. So basically you are adding as new features A times B times C, B times C times E, D times A times C, and so on. Okay, and after that you can run your weak model on the new set of features, and in many cases it actually helps and it gives much better results. So this is one way to fix your problem. Okay, but to do this, we actually need to know how many features do we have in the end. So how many features do we add? And basically what we do is that for each new feature, we pick a K combination of old features. Okay, so we need to count the number of combinations. And there is a short formula for the number of combinations. Actually, n choose k is equal to n factorial divided by k factorial multiplied by a minus k factorial. Okay, let's review the proof of this. It's very similar to the previous examples, but let's review it in general. So we need to count the number of subsets of size k of a set of size m. Okay, there are n choices for the first element, n minus 1 choices for the second element, and so on, n minus k plus 1 choices for the last element. And this gives us n times n minus 1 and so on times n minus k plus 1, that is n factorial divided by n minus k factorial options. But these are actually k permutations, not k combinations, because we have picked the ordered sequence of k elements. Okay, in other words, we counted ordered subsets instead of unordered. So how can we fix this? Note that each subset is counted as many times as there are ways to order it. And how many ways do we have to order a subset? There are k factorial ways to order a subset of size k. So we counted each subset k factorial times. And so to get the final answer, we need to divide the previous result by k factorial, and this gives us the actual result. The answer is n factorial divided by k factorial multiplied by a minus k factorial. Okay, in this week we started to study combinatorics. And we started with some simple observations, right, like rule of sum or rule of product. And building on them, we get to a more complicated settings like tuples, permutations, combinations. And we reached rather non-trivial questions of counting combinations, for example. And next week we will proceed with combinations, and we will see that they have nice and interesting properties.